I want you to look at a simple sketch of a steel rod. It is thin, silver, and threaded at the ends. On its own, it does not look like much, but in the world of structural engineering, this rod is a lifeline. It is the bridge between gravity and stability. Today, I want to talk about a specific moment in history where the way we connected these rods changed everything. We are looking at the physics of the double rod connection, specifically within the context of the box beams used in the Hyatt Regency in Kansas City. When we build something, we often think of the big picture, the glass, the concrete, the soaring ceilings, but the integrity of a structure often lives in the smallest details, in the places where two pieces of metal meet and decide how to share the weight of the world. In the late 1970s, the design for the hotel featured beautiful, suspended walkways that crossed a vast open atrium. These were not supported from below, they were hung from the roof by long steel rods. Imagine a swing set, but on a massive architectural scale. The design called for a series of box beams, basically two steel C-channels welded face to face, to act as the floor supports for these walkways. A single, continuous rod was supposed to pass through the upper walkway's beam and continue down to the lower one. It sounds straightforward. On paper, the math worked. The weight of the lower walkway would pull on the rod, and the weight of the upper walkway would also pull on that same rod. The rod itself was strong enough to handle both. But there was a problem that did not show up in the initial calculations. It was a problem of practicality. To install a continuous rod that spans several stories, you have to thread the entire length of that rod. You have to spin a nut all the way from the bottom to the middle to support the upper walkway. In a fabrication shop, this is a logistical headache. So, a change was proposed. Instead of one long rod, why not use two? One rod would go from the ceiling to the upper walkway, and a second, separate rod would hang from that upper walkway down to the lower one. It seemed like a minor adjustment. It solved the threading problem and made assembly much easier. But in the world of physics, there is no such thing as a minor adjustment. When you move from a single rod to a double rod, you are not just changing the hardware, you are fundamentally rerouting the flow of force. In the original design, the nut under the upper walkway only had to support the weight of the upper walkway itself. The weight of the lower walkway passed right through the beam via the rod. But with the double rod system, something happened. The upper rod now had to support the nut for the upper walkway, and that nut now had to carry the weight of both levels. The force on that specific point, the place where the rod met the box beam, doubled. Think about a person hanging from a rope. If a second person grabs the rope above them, the rope feels the weight of both, but the first person's grip only feels their own weight. Now, imagine if the second person grabs the first person's ankles instead. Suddenly, the first person's arms have to support both their own weight and the weight of the person below them. That is exactly what happened to the box beams. The steel flange of the beam was never intended to be the middleman for that much force. The evidence points toward a specific mechanical failure. The nut did not break and the rod did not snap. Instead, the box beam itself began to deform. Under the intense pressure, the steel channels started to pull apart. The nut was essentially being pulled through the beam. It is a phenomenon we call deformation, but in this case, it was the result of a load path that had been unknowingly compromised. The common view of this event often focuses on the math, but the missing angle is often the communication between the designer and the builder. A sketch on a table does not always account for the reality of the shop floor. When the fabricator suggested the change, the implications for the load transfer were not fully reevaluated. The system was under pressure not just from gravity, but from the schedules and the ease of construction. We often look for a single villain in these stories, but the reality is usually a series of small logical decisions that lead to an illogical conclusion. The lesson here is not just about steel and rods. It is about the as-built reality. It is a reminder that every connection is a conversation between materials. If we change the language of that conversation, we have to be prepared for the result. The physics of the double rod connection remains one of the most studied cases in engineering because it highlights how a simple change in geometry can lead to a shift in capacity. As we look at these pencil sketches of beams and rods, we see more than just lines. We see the paths that force takes. We see the responsibility of the engineer to follow those paths to their very end. It is a quiet, sober reminder that in our built environment, nothing is truly minor. If you find these deep dives into the mechanics of our world interesting, I invite you to stay a while. Let us keep looking at the sketches, the evidence, and the lessons left behind by the structures that came before us. Thank you for listening. Please consider following for more engineering case files and forensic analysis.